Welcome back. We're now ready to start the second chapter of the course, which is broadly speaking about data analytics, but more specifically about linear algebra, beautiful branch of mathematics that will form the basis for many things that you think about in data analytics, data science, machine learning, AI, computer vision, computer graphics, robotics, natural language processing, and so on and so forth. So in addition to creating the mathematical machinery and computational machinery to do some basic data analytics, it really forms the basis for many courses and things that you will do in the coming months and coming years. So let me start with what is probably one of my favorite quotes of all time. It is by the brilliant mathematician and academic Gilbert Strang in the cover of his particularly beautiful linear algebra book. And it says, "Linear algebra is a fantastic subject. On the one hand, it is clean and beautiful." I love this quote because it really sort of encompasses exactly how I think about linear algebra. It is clean, it is beautiful, and I would add incredibly powerful. It's one of my favorite branches of mathematics. It's something that is fairly accessible if you have basic understanding of algebra. And it forms the basis, as I said earlier, for many, many things that you will do in the general field of data science, data analytics, and computer science. So let's just go ahead and dig in. At its core, what linear algebra is about is solving simultaneous linear equations. So here are two equations in two unknowns, x and y. And your job is to tell me what are the values of x and y that simultaneously satisfy that equation and that equation. Now obviously, if we only had one equation, x plus y equals 5, and I said, what values of x and y satisfy it? Well, there's all kinds of values, 2 and 3, 4 and 1, 5 and 0, et cetera, et cetera, et cetera. But with two equations and two constraints, there's maybe not so many, although you'll see a little bit later, it's going to depend on the nature of the equations. So two simultaneous linear equations, solve for me, please, the unknowns. Now, why do I say that these are linear equations? It's because the unknowns are related by addition or obviously subtraction. So I'm not multiplying x by y, I'm not dividing x by y, I'm not exponentiating x by y. The unknowns are only related by addition, and the unknowns can be multiplied by known scalar values. So I can't say x times y, but I can say 2x. I can say minus y, and of course everything on the right-hand side of these equations is of course known. Okay, so those are two simultaneous linear equations and two unknowns. The unknowns are related by addition, and the unknowns can be multiplied by scalar values. Okay, so how do we solve these equations? Well, there's three ways we are going to talk about. The classic way that you've already learned and maybe have forgotten, which is the algebraic. That's the thing that you probably learned in grade school. There's the geometric picture. What is the geometric picture? What do these equations correspond to in terms of geometry? And then, of course, there is the linear algebraic. And I think what you'll see is the linear algebraic formulation is particularly nice for a number of reasons. It extends beyond two equations and two unknowns. It has this very nice mechanism for talking about when is there a unique solution, when are there multiple solutions, when are there no solutions. And it, of course, will form the basis for many things that we want to do beyond this when we go beyond just simple simultaneous linear equations. But let's start with the algebraic picture to remind ourselves how we solve these and just to sort of re-exercise that algebra muscle that may be a little bit rusty at this point. Two equations, two unknowns. Please find for me the values of x and y that satisfy both equations. So how am I going to do that? Well, if I look at one of these equations, there's two things going on here, and I can't just keep guessing at values. So I've got to start to sort of figure out how do I isolate one of the values, and then from there maybe I can get the other value. So what if we take this equation, x plus y equals 5, and we isolate it by pushing all the one unknown to the right-hand side and leave the other unknown on the other side. And I could have done this as y is equal to 5 minus y, or x is equal to 5, y is equal to 5 minus x. So it doesn't matter which direction we do it in. I just did it in this direction. So what have I done here? I've said that whatever the value of x and y that satisfy this, x is going to be equal to 5 minus y by simply subtracting y from both sides of the equation. Good. Why is that helpful? Well, it's helpful because I can take that value of x, 5 minus y, and I can shove it into this equation. So first of all, why am I allowed to do that? Well, I'm allowed to do that because I'm looking for a solution that simultaneously satisfies that equation and that equation. So if x is equal to 5 minus y, which it does in this equation, well then x is equal to 5 minus y in this equation. So I can take that constraint and I can shove it into that equation. Now why is that helpful? Well, now it's helpful because we'll simplify this in a second, but now you see I have one equation and one unknown. And that's super easy to solve because everything remains linear, of course. So what did I do here? I took 5 minus y and I shoved it into right there, because that's x. So now I have 2 times 5 minus y is equal to 1. There's only one unknown here. I have factored out the x, or I've isolated the y. So let's go ahead and just simplify that. That should be pretty easy. Let's multiply through by 2. So I've got 10 minus 2y minus y is equal to 1. And now my job is to solve for y. So I put all the constants to the right-hand side, bundle up all the y's on the left-hand side, and then do whatever division I need to based on the scale factor that is multiplying y. So 10 minus 2y minus y is 10 minus 3y. So I've combined those now into one unknown. Of course, I can bring the 10 over, subtract 10 from both sides. I have 1 minus 10 is minus 9. Minus 3y is equal to minus 9. Please divide by minus 3. And of course, y is now equal to 3. So we've got sort of half the picture. We're almost there. We know that whatever the values of x and y are here, y is going to be equal to 3. And now the question we want to ask is, for these two simultaneous equations, when y is equal to 3, what is x? Well, now it's easy because we've gotten one of the unknowns out of the way. So I can take this equation and say, well, I know y is equal to 3. Or I can take this equation and say I know y is equal to 3. So x plus y equals 5 becomes x plus 3 is equal to 5. 2x minus y equals 1 becomes 2x minus 3 is equal to 1. Now, remember again, whatever x and y we come up with, it satisfies both equations. So both of these must be true. So let's go ahead and figure it out. So here, if that's true, then x, of course, must be equal to 2. Subtract 3 from both sides. So x is equal to 2. We're done at this point, and we're going to go back and verify this. But I should be able to solve for x over here too, and it better be 2. So I've got 2x minus 3 is equal to 1, 2x is equal to 4, x is equal to 2. So one way or another, I can solve for x once I have a solution for y. Now, of course, once I have this, I should be able to confirm that it's correct. There's no reason to guess with algebra. So 3 plus 2 is equal to 5. Yep, good, that works just fine. And 2 times 2 is 4. Minus 3 is equal to 1. That satisfies that. So 3 and 2 are the solution to that system of linear equations. And all I did was the classic algebraic story where I took one of the equations, and it could have been either one, and I isolated for one of the variables. It could have been either one. I substituted that into the second equation, solved for one of the unknowns, and then back substituted in to get the other one. Okay? Now, here's a question you might want to ask yourself is that unique? Is there more than one solution? How do I know there is a solution? So that picture doesn't come immediately obvious in this algebraic solution, but it will become more obvious in both the geometric solution that we'll do next and the linear algebra solution that we will do after that. So hold on to that question because we'll come back to it. All right, let's just do one more example to just exercise that algebra muscle a little bit more. Two linear equations and two unknowns. X and y are clearly the unknowns here. It is linear, the x and the y are being added. It is linear, the x's and the y's are being added. The unknowns are being multiplied by known scalar values, 6, 2, 3, minus 2, and of course I have some known constants over here. So of course these are linear equations, and I want to find again the value of x and y that satisfies both equations. All right, so let's play the same game. Take the first equation, 6y plus 2x is equal to 24, and let's solve for x in terms of y. So let's bring the 6y over to this side. So I've got 2x is now equal to 24 minus 6y. And I'm now going to divide by 2. So x is equal to 12 minus 3y. So whatever value of y I'm eventually going to solve for, I shove it right into there and I get an answer for x. Well, how do I get that value of y? Well, now that I know that x is equal to 12 minus 3y, I can go back into the second equation and substitute it into there. I will again get one equation and one unknown. And now I can solve for y, and then I'll back substitute in. So let's just go ahead and do that. I'm going to take the 12 minus 3y. I'm going to replace x with that. So I've got 3y minus 2 times 12 minus 3y is equal to 3. And now let's just go ahead and do the algebra. So 2 times 12 is 24. There's a negative sign there, so I get a negative 24. 2 times 3 is 6. There's a negative sign there and a negative sign there, so I get a plus 6. So I've got 3y, and I've just flipped the terms to put the y's next to each other. Plus 6y minus 24 is equal to 3. Let's bring the 24 over. That's the constant, so I add 24 to both sides of the equation. I get 3 plus 24 is 27. 6 plus 3 on the y is equal to 9. 9y is equal to 27. Divide by 9, of course. Y is equal to 3. Good. Now, once I have y is equal to 3, I'm home. I bring that back up into the first equation. 12 minus 3 times 3, which is 9, is equal to 3. And I can back substitute it and make sure I got everything right. So let's just go ahead and do that. So y is equal to 3, 18. X is equal to 3, 6. 18 plus 6 is 24. Let's just verify the second equation, even though we're sure it's right. X equals to 3 minus 6 here. Y is equal to 3, 9. 9 minus 6 is equal to 3. You can always check your work. If you made a mistake in the algebra, it's going to come out eventually. These things aren't going to. The math won't work out. Okay, so that's the grade school algebraic picture. Two equations, 2 unknowns, relatively easy to do. What would you do, by the way, just think this through, if you had 3 equations and 3 unknowns? Well, I've got x, y, and z, x, y, and z, x, y, and z, and they're linear. So I'd have to isolate one of the variables in terms of 2 of the other ones, shove that into the second equation. Now that equation has 2 unknowns in it. Isolate that in terms of one variable in terms of the other, shove that into the third one, and then start backing your way out. So things get a little messier as you start to go to 3 equations, and then 4 is even messier. So this algebraic formulation works pretty well for 2 equations and 2 unknowns. Not a lot of algebra has to be done. But once you get into higher order systems with more unknowns and more equations, things start to get a little messy. So that's where one of the really nice things with the linear algebra is going to help us. It's going to scale very nicely to arbitrary unknowns. Now, I could just jump right to the linear algebra, but I want to sort of take a little break here and show you the geometric picture here. Like, what are we doing? What does it mean when we're asking for the value of x and y that solves those 2 linear equations? Sure, we can think about it purely algebraically, but I think it's nice to have a sort of picture in our head. So when we come back, we're going to look at the geometric solution or the geometric picture for solving simultaneous linear equations. And for now, we'll stick with 2 equations, 2 unknowns, and then we'll start in on the linear algebra. All right, we'll see you in a few minutes.